Hello everyone. In today's lecture, we'll talk about the shortest path. So we will consider two main algorithms that find the shortest path. The first one is the Dijkstra algorithm, and second one is Bellman force algorithm. So let's start. But first, we need to talk about why do we need shortest path? The shortest path is mainly used on daily basis on finding the shortest path between 2 points. Let's assume that you are located here and you want to reach this point, and you want to go in the fastest way possible. So what do? You can open any map like a Google map or to GIS, and you enter the locations that you want to go, and the map will show you the shortest path. But how do you do that? They apply some algorithms, and in the end they show you the result. So let's define what is the shortest path problem itself. So shortest path can be applied on a directed graph. In the shortest path, we have usually the source and destination t. Cost VW is the cost of using h from vertex V to the vertex W. And in one word, in one sentence, the shortest path is the process of finding the shortest path, finding shortest directed path from S to the T. And the cost of the path is the sum of r costs in a path. So here we have um, directed graph. Here we have source S and destination T. And if we apply some algorithm to find the shortest path here would be the cost of it would be equal to the 48. So here we just sum up all the edges that we have all along the way, and then we can find the cost. So the shortest path was initially started to discover around 1950s. So first step was done by scientist Schimbel in 1955. He wanted to apply the shortest path in information networks in mean-sum algebra. Then later on, by Ford 1956, he wanted to find the shortest path in economics of transportation. But the biggest breakthrough was done by Bellman in 1958. He used dynamic programming to find the shortest path. And on 1959, by Moore, he used some shortest path algorithms in routing the long distance telephone calls for Bell Labs. So it was starting of the phone, the connection of the phones. So in 1959, by Dijkstra, he found very simple and fast version of the fourth algorithm. The shortest path can be applied, of course, not on the directed graph. It can be applied on the undirected graph. In a shortest path, we have single source, then all pairs, like finding the shortest path between two vertices. All the costs are usually equal or bigger than zero, and in the points in the plane, it can be found the distance between the 2 points can be found by Euclidean distance equation. So in the shortest path, we have a process which called edge relaxation. So what kind of process is that? Let's assume that we have found the some shortest path to some point, but after we later on we have found that there is actually even shorter path to that point. Then we need to update our records and rewrite our data structure. So, for example, let's say that we have some data structure called WT, where the index W is some vertex. So it means that it's the shortest path from source S to this W. And at some point, we have found that actually there is a shorter path from to the W, where it's the shortest path to the V. plus the cost of the edge from V to the W. So we rewrite these values and we say that the previous vertex to the W is V. So for example, let's take a look on this graph. We have the shortest path from S to the W, so it's equal to the 47. And but later on, we found that actually the shortest path from S to W is not 47, but it's equal to the 44. So if we go in the shortest path from the S to the V, it's equal to the 11, and the edge of the from between V and W is equal to the 33. So we remove this previous value and we say that actually the shortest path from S to W is equal to the 44. So now let's take a look on the Dexterous algorithm. So Dijkstra's algorithm finds the shortest path from the S to all other vertices, and shortest path from S actually is form in the end it forms a tree. So here we have some graph. We have source S and destination T. Initially, the Dijkstra's algorithm we put into our set of vertices S, and we consider all the neighbors of the S, which is the 2, 6, and 7. And among all these vertices, we go to the vertex that has the lowest cost at this point. So lowest cost here is equal to 9, so we go to the 2, and we add 2 into our set. And on the next step, we consider the all neighboring vertices of our set. So here it's 3 with the cost 24. Then from S to the 6, it's equal to the 14. And from S to 7, it's equal to the 15. But here we need to also consider that it's not only 24. It's actually 24 plus 9, so it's 35. So 33, sorry. Then among all these options, we choose this 14 and we go to the 6. Then we add 6 into our set. And on the next step, we need to consider the all neighbors of this set. And the process is happening until we cover all the vertices and we um, reach our destination. So now next, let's take a look how do we implement this algorithm. So initially we um, create we create some data structure. We can use array or we can use hash map. And in this data structure, we will store the cost of the shortest path from the S to some vertex. And initially, we give the all like cost to all vertices is infinity, and the shortest path from S to the S it's initially equal to the 0. Then we insert all vertices V into our priority queue. So here in priority queue is actually binary min heap. So binary min heap is the structure where on the top of our heap we have the value with the lowest among all the possible values that we have. So in priority queue we use it with priority to the V, and we repeatedly delete the node V from our priority queue that has the minimum cost. Then we add V to our set, and for each VW, we do the relaxation process. So here is the code of our implementation. So our while loop runs while the priority queue is not empty. Then we take the vertex with the lowest cost, and then we consider all the neighbors or all the adjacent elements of the V. Then we have another while loop that goes through these adjacent values. And if at some points we have figured out that actually there is a even less cost to the W, then we rewrite this value and we says that the previous vertex to the W is equal to the V. The disadvantage of the Dexterous algorithm is that it doesn't work with the negative costs. So, for example, let's say that we have this kind of graph, and we need to find the shortest path from the S to the V. Initially, when in our set we have only S, we have two edges. We have two neighbors. One edge goes to the X, and second edge goes to the V. And here we have cost 4, and direct path has cost 2. And the Dijkstra algorithm would say that the shortest path from the S to the V with the lowest cost is this path. But actually, the path with the lowest cost would go in this direction, because here we have the negative value. So it would be 4 plus 6 minus 9, and it's equal to the 1. But the Dexter's algorithm wouldn't find that it's right path. So we need to find the algorithm that works with the negative costs. So this algorithm can be used with the dynamic programming. So in dynamic programming, again, we use some data structure. We call it WT with and shortest path to the V, and initial value is infinity, and the shortest path to the itself, to the source point, is equal to 0. Then we run our loop V times, and we do the relaxation process for each edge. So here we have loop that runs through all vertices, and each iteration we call phase I. Then we have another for loop that runs all the vertices, neighboring elements, and if at some point we have the cost with the lowest value, then we update our lowest cost path. So the time complexity of this algorithm is E multiplied by V, so it's big theta E multiplied by V. So E is the number of edges and V is number of vertices. So we can actually optimize this algorithm because the time complexity is not as good as, for example, the Dexterous algorithm. We can optimize a bit, and the optimization is called Bellman-Ford-Morse algorithm. So in Bellman-Ford algorithm, we if the shortest path V doesn't change during phase I, then we don't relax any edges of form VW in phase I plus 1. So here we use the queue of the nodes that we have changed. So again, we have while loop while this queue is not empty. So recall that queue works in the principle of the first in, first out. Then inside of this while loop, we deck our queue, and then we take all the neighbor elements of this V. And while this iterator has the next element, we again do the relax process of the V W. But actually, this algorithm still runs in EV time complexity, but in practice, it's much faster. And also a very important point here that we need to enqueue the W into our queue so we can discard our duplicates. So Bellman-Ford-Morse algorithm is actually can have the next problem. When we have some negative weights, Um, and if we have the cycle, then we can run this cycle many times, and then we can decrease our pass infinitely. So, for example, let's say that we have this kind of graph, then we go from vertex 2 to the S, and the S has a loop to itself, like with a negative value. So let's say negative 4. And it can do the cycles many times, and it can decrease the cost of the pass, which is actually not correct. And um, in a negative cycle, we can detect the negative cycle by the next properties. If any node v is n-q'd v times, so n-q'd means that we have included it into the q v times, then there must be negative cycle. So v means the number of vertices. Uh, but we can use our lead structure uh, of the previous elements. So if you remember here, we keep tracking of the previous elements of each vertex. For example, if we reached vertex W from the vertex V, then we say that the previous element of the W was actually V. And if we can trace back by these records, then we can find the cycle. Here is a um, comparisons of our algorithms. So Dexterous algorithm, actually initially it was used with arrays to keep track of the values. And the classic Dexterous algorithms worst case time complexity is v square. The best case also v square. The memory, the space it takes is linear. So we just um, take, for example, if we have v number of vertices, then we will use v number of memory space in our memory. If we use binary heap, we have some kind of optimization. So in that case, the time complexity e by log v, and the best case is linear, and the space still the linear. If we use just the dynamic programming, where we can use the negative weights, then the worst case is equal to the e multiplied by v. Base case also e multiplied by v. The time complexity, the space complexity is linear. And in optimized dynamic programming, which called Bellman-Ford-Morse algorithm, the worst case is EV, but in practice, actually, it's linear time complexity since we use the queue to maintain the nodes that we have changed, and the space as well the linear time complexity. Here we have two remarks about using the dynamic programming. So the negative weights makes the problem harder. So as you can see, if we have negative weights, then the Dijkstra's algorithm doesn't work. We cannot use it. The Dijkstra's algorithm will show the wrong answer. And negative cycles makes the problem intractable because we can run the cycle many times to decrease the cost, but actually it's not correct answer. So um, that's it for today. Thank you very much for watching. See you.